There were at least 3 people that did this. What is wrong if I ask you to do this? Integral of 7y over dy. Is there an issue there? Yeah, I love it. That's a beautiful way. You can't do that. Yeah. Well, there's your problem, Jeff. Can't do it. What's wrong with that? Besides, it doesn't make any damn sense, right? The integral notation, the integral symbol is not this. The integral symbol is this. It's what I call bookend symbol. This does not make any sense without that. And it seems like maybe some of your teachers did not make a big enough deal about this. This should never be missing. And now you're starting to understand why. Because it totally depends. Am I integrating dx? Am I integrating dy? In 180 and to most of a degree in 280, it didn't really matter. It was always inherently understood what you were integrating with respect to. So you could sort of forget that and not realize how big of a deal it is to forget that. You guys kind of with me? Plus, it can't be on the bottom. Okay. You guys with me? I'm sorry. All right. I'm a little too far removed from this now, but anything, did I answer the question? I'm not even sure. Anything else from the test? I'm trying to remember what else happened. Yeah, one thing I want to say before I forget. Do it, Jeff. Sure. All right. I try to make a big deal out of this when I taught 180, 280. Is that natural log?
No.
Hell no, right? The only time it's natural log is if it's something to the -1 power. This is -2, right? You can pull a 1/2 out of the way, it's just a freaking constant, get it out of there. It's a -2 power, that's not a natural log. If I had this, will that be a natural log?
Yeah.
Hell yeah. Because now the u sub is going to make the bottom u, that's u to the -1, natural log, right? You guys see that? So I saw a few too many people kind of like flying past all the right work to get the answer quickly, which is the wrong answer. So be careful. It's not automatically natural log. That would not be natural log. Right? Okay. And also, none of the problems require trig sub. Right? Now, I think there was one person that did trig sub and got it right, if I remember correctly, but dear God, that was a lot more work than I wanted. Again, the reason I say rule out u sub is because there's a lot of u sub problems you could use trig sub. I could use trig sub on this problem. I could use trig sub. I don't want to, and I don't have to because it's freaking u sub. So rule out u sub. Some of you guys did by parts, I think on the quiz, I can't remember. You didn't rule out u sub. So always go, is this a u sub? Prove to yourself it isn't before you try something more than u sub. Does that make sense?
Yeah.
All right, I'm sorry. Somebody had a specific question. Did they talk over something? Anybody had a question? I think I got everybody's question. Okay. Anything else from the test while you're looking at it? All right. As always, anytime I grade a test, if you have an issue with the grading, like it doesn't add up correctly, which is hilarious for a math teacher when I don't add, it's awesome. It's one of the best things. You're like, I got an 80, but I only lost 10 points. Oh shit. Okay. Let me know. If you're not sure why I took off how many points I did, just ask me, not a big deal. Okay. Now what really sucks is what happened recently is sometimes I'll forget to take off a point or something, and then somebody else notices. I'm like, well shit, they got lucky, right? I'm never gonna take the grade lower than what it is right now. Even if I'm like, oh, I completely forgot to grade that problem. It should have been -10. I'm not going to suddenly do that to you. Number one, I don't want you to be afraid to turn in corrections, right? If I did that and you turn in corrections and I'm like, well, -20, oh, well, too bad. No, that would be so evil. I'm not that evil. 10 years ago, I said, wait 10 years. I'm not quite there yet. All right, just got to burn out just a little more and then I'll be evil. Oh, damn it. I'm sorry. Anything else? I'm sorry. Anything else? Okay. And if you came in after I talked about it, these are some ideas for ways to study more fully. Because the higher up you get in mathematics, the more important the concept becomes. You guys with me? Concept's important, period, but the higher up you get, the more important concept becomes. So you want multiple ways to consider something so that it will actually match with the way you look at things. Does that make any sense? And I'm just one person, and I am nowhere near the best teacher. I've got my own perspective. I try to get out of that as much as I can, but I'm limited. I'm just a human. So you want other humans that have other perspectives. Okay, enough of that. All right. What I want to do, if there's no other questions, we are going to talk about chapter 3, but I am going to go ahead and I'm going to make chapter 3 extra credit. 3:1, 3:2, extra credit. Is everybody here? It's kind of funny because I look back at the last time I taught this course and I didn't do 3:2 before. And this semester I decided to throw 3:2 in there. So it's not even really a part of our thing, but 3:1 and 3:2, extra credit. There are a couple of things from those sections I definitely want to talk about. One thing about things like section 1.3 and chapter 3, it really is dependent on where you go from here. So for example, I know this in the survey, I asked this, but is anybody majoring in a field that's not mathematics? Like, how many of you guys are majoring in mathematics, by the way? Okay. You know. Yeah. Anybody majoring in a science other than math? Because math is the most fundamental science. What are you majoring in? Chemical engineering. Yeah, that's not like this. Yeah.
Mechanical engineering.
Geological oceanography.
Oh, kick ass. Not to shit on anybody else's name, sorry. Just like the way that sounded. All right. As you get into your further courses, higher up courses in those fields, you will have definitive adjustments to the processes we talk about. If you go into physics, we do this. We just do it in very kind of different ways because we can make it more specific, right? I'm teaching you general conceptual theory. When you go to a specific department, division, class, you can kind of modify those. Are you guys all with me? Okay. So section 1.3 and chapter 3 are important because they tell us what we use differential equations for in real life. But really, the ones you're going to focus on, you're not even going to quite do them the way that we do them here. You're going to kind of modify the procedure. A good example of that is I teach statistics, Math 160, math stats. We also have economic statistics, psychology, we have sociology, we have business statistics, right? Business stats. They're all 215. They teach the same concepts I do, just in modified ways. Modified to fit what they need it for. Okay. So, the couple of things I want to say from chapter 3. Just to remind you guys, chapter 3 really is sort of like 1.3's next step. And section 1.3 is everybody's favorite section. You're all like, I don't care about salt in the tank. Okay. If you have no idea what I'm talking about, you haven't tried. So the most fundamental thing about how differential equations come to play with other fields is very often we have a relationship we notice that's dependent on the rate of change of something. So the flow of water through a dam, how quickly the temperature changes across some medium, so forth, right? So these could affect whatever it is I'm looking at. So when I set up equations to model that situation, I'm going to have differential equations because they involve the rates of change. The most basic one that we've already seen before is growth and decay. And I liked a couple problems in section 1.3 that talk about, okay, you have birth rates. What about death rates? How do you fill that in? So that's the idea of a basic idea and its solution, and then you bring other variables in to see how that changes. And something further down the line, something called perturbation theory, which is you solve the easy answer and then you perturb it with another variable. And you perturb it with another variable and you just sort of instead of solving the whole thing, you just sort of add the variables in at the end and go, okay. So growth and decay, the basic idea of this is the rate of change of the amount of something is proportional to the amount that's there already. So just like I could create the equation of a circle by saying a circle is a collection of all the points that are equidistant from a certain point, the center. That leads to the circle equation. You guys kind of with me? Have you ever heard what I just said, right? The equation of a circle is all the points that are equidistant from a certain point, and that's R. Looks like a very satisfied circle there. You guys with me? So the center is HK, blah, blah, blah. You can get to the x minus h squared, blah, blah. Good old Pythagorean theorem, all that kind of distance formula. You guys kind of with me?
Yeah.
So the idea creates the equation. The idea of growth and decay rates is the rate of change of the amount of something is proportional to the amount that's there. Okay, I like it. So if you talk about population, that makes sense. The more people there are, the more people that can make more people, so the quicker the population could grow. And it's absent the other variables that can come into play. You guys semi with me? Okay, maybe. Could you solve this very quickly? Or, solve it, let me say it like that. Can you solve this? What's a good first step to try to solve? What form is that in?
Separable.
Yeah, what else is it, by the way? It's autonomous. Kick ass. Yummy. So, I want you to notice, we've done enough phase portraits now that you get stuff that looks like exponentials. Does anyone know what this kind of shape is? It looks like an arctangent, but it's also like a logarithmic, like a, not logarithmic, what am I just had the name of it and it's gone. It's gone, it'll come back. So very often when you see autonomous, you're gonna get exponential, logistic, there it is. It's got the word log in it, that freaked me out. Logistic formula, it's got a ceiling to it. You guys kind of with me? So if I plugged in to this equation, made it much worse, could we just grow unbounded on this planet? What? Unbounded. Unbounded. If we grow enough, do you understand that every person would get like exactly the size of their feet to stand on? Are you with me? If we grew too much, do you understand? Please tell me you understand. We cannot grow unbounded. So if I included the variables that relate to the resources, the space, are you guys kind of with me? There are other variables besides the population. I would get a formula that would have a ceiling to it. Yes?
I tried doing some 1.3, and how do you even know what those variables are going to be? How do you know if it's going to divide, subtract, add, multiply? Those end up getting kind of crossed in my head. It's so hard.
All right. If you give me a specific example, there's the very early problem about the birth rate and the death rate.
Yeah.
And the thing that people mistake is that the B and the D they give us are themselves rates. So they are already rates of change of something, right? So they each equal their own KT, for example. But you have to give me a specific thing to work off of.
Yeah, it's been a while.
Okay. All right. Can you solve that? Does anybody solve that, or have I been talking too much? Probably. What's the first step to solve this? Yeah, divide by A. I could divide by K, but I'll just divide by A and make this side as easy as I can, because the KDT is going to be easy, right? So we have choices where constants go. Y'all are with me on that, right? So if there's a 2 floating around, I could put it either damn side I want to. It's going to end up the same answer, but one choice could be easier to work with than the other. So I'm going to stick that over there because this side is an easy interval. I'm not going to stick it over here because that side's a gross interval. Not gross, but worse. So obviously, what's this about? Natural log of A, and I'm not going to put absolute value because in this case, this represents like a population growth or something. I can put that in. No. That's the amount of something that I've got, right? Yes?
Sorry, is that KDT?
K, yeah, my poor little K dude is mutated. Okay. And then over here we get KT. Let's see.
Plus C.
Now, something that still eludes people, so let me do this all the way out. If I raise e to both sides, so tilde ln, how do I deal with this? Yes, times e to the c, because I add powers when I multiply bases. So then this becomes a equals c2 e to the kt, and of course normally we call c2 a0, because when do I get a to be a0? What would I make t? What would I make t in order to get a0 is the answer? 0, right? You guys all with me on that? So of course it makes sense, I'm going to call this original amount, or the null amount, the beginning amount. Okay. Let me stop for a minute. That one's not very fascinating. There are several problems in that section that require no DE work, because you're just going to take this equation and work with it directly. That equation is the result of a DE solution, but then you can just use it for a lot of things. You can figure out what K is if they give me enough information. So for example, if I told you that after 3 hours, there is 25% of this amount left, could you solve for K?
Yeah.
Do it. Oh wait. I can name that to it in 2 notes. Yeah, that one for sure. Yeah. Oh yeah, it was good. That's true. Did I? I did. Sweet. I don't know. Figure it out. All right, so let me see. Let me catch up to you guys. What the hell are you doing? What's going on? So when I plug a 3 in, that results in 0.25% of what was there at the beginning, right? So anytime there's you end up with half of it, or it doubles or whatever, the A0s are going to cancel, right? That's awesome. Go away. Yeah. So in that case, I don't even give a shit what A0 was. It doesn't matter, which is beautiful, right? So you get 0.25 equals e to the 3k, and then of course to solve for k, you just natural log. So, you got this right here, John. 0.25 equals e to the 3k. Take ln of both sides. Ln of 0.25 equals 3k. Divide it by 3. You get k. Now, real quick, is this a growth or a decay?
Decay.
Decay. In which case, k really should be negative, and of course, this is negative because natural log of 0.25 is. What's a natural log look like? Yeah. Do it again. There you go. Okay.
So like natural log is 0.
Wow.
So it's below.
Right? You with me?
Yeah.
What's this?
1.
1.25 is in between 0 and 1, and the output's negative. So k will be negative like I knew it should be because this is freaking decay. How do I know it's decay? Because it said so much is left, so I'm losing some of it. So this could be like radiative decay, right? You guys all with me? Or just people moving away, maybe, in a population, right? Yeah, like I had a problem real quick on the test, on the pre-calculus test they gave, which had nothing to do with this yet. But a certain number of teachers, there were 11 teachers in 2000, and then there were 3 teachers in 2010. Find the linear equation. Somebody wrote, "Did they all die?" No, they retired or moved away. They didn't die. All right, and I got worried for my own safety. Math teachers must die. Is that all right for that? So there are like 2 or 3 problems that are really just figuring out what K is, and then they ask you, all right, after 7 hours, how much will be left? Then you just throw a 7. So some of this will be very straightforward. If, you know, and again, you see the same old things kind of come out, so that's why it gets a little bit boring, but like again, they're gonna have some more salt in the freaking tank, and you're like, who are these people with the brine happening? But one thing I do like is Newton's law of cooling. If I set a coffee cup out in a room, it cools down until what? All right, so I need an equation where the rate of change of the temperature of the coffee in the mug becomes 0 when it reaches the same temperature as the room it's in. Correct? So that would say, let's see, the change in the temperature over time is proportional to, let's see if we can figure this out. So when will something cool down faster? So if I put a nice steamy thing of cocoa in a room, it's going to cool down. If I put it in the freezer, it's going to cool down quicker, right? In fact, it's a little bit, that's not quite what I want to say. Let's say I put a steaming hot thing of cocoa in a room, and next to it I put, what do you got, Jeff? I don't know. Something, huh? Yes.
Is that when the difference between 2 things is greater?
Yes, thank you. Okay. So when the difference between the temperature of the thing that's cooling down or heating up and the temperature of the environment it's in, when that is the greatest, it's going to have the highest rate of change in temperature. So the change in the temperature is proportional to the difference between the temperature of the thing, that's the variable for the temperature of the thing, minus, in this book they call it TM. I think M is medium, maybe? I can't remember. I'm not sure why they use M. Okay. How would you solve this? This gets kind of repetitive because what do you think the solution to this would involve? Is this autonomous?
No.
Do you see this variable here? Okay, so is this autonomous?
Yeah.
Yes, okay, good. You with me? Is it separable?
Yeah.
It's automatically separable if it's autonomous, yes? I like it. Because whatever the shit's here, I don't even care. It's all a function of that variable, so I can always just throw it underneath. It's going to involve what when I solve it? What did we just get for the growth and decay? An exponential, right? Logarithmic that would lead to exponential, correct? This is going to look the exact same way. So you're going to have very similar problems where they're going to give you a situation, you can figure out what the K is, and then they're going to ask you, what if you wait another 10 minutes or whatever? You guys semi with me? Okay. And again, that's if you want to do it, because again, in case you missed it, 3.1 and 3.2 are extra credit. The last thing I want to talk about chapter 3, not for the day, is, let's do a problem. This problem hits a little different than it used to. Virus spread in a population. So let's say that a student comes back to college. And the college has 1,000 students, right? Very exclusive little college. And then we're curious about the rate of spread of the virus through the population, right? So I want to know, let me use the same, did they just use a, oh, okay, sure. So X would be the number of students that have the virus. So not only does the rate of spread of the virus, now what do you think that depends on? I mean, now to be honest, there's a lot of variables that we throw in there. But the most basic thing it depends on is the number of people that have the virus. But doesn't it also depend on the number of people that don't have the virus? Are you with me? So there's a proportionality here. So it depends on the number of people with the virus. And then of course, what would the number of people without the virus be?
Not understanding.
There's 1,000 total, there's X people with the virus. So 1,000 minus X. Kick ass.
Why is the X out in front of the parentheses?
So it makes sense that it's proportional to the number of people with the virus. It makes sense for that.
Mm-hmm.
But it's also varying as the number of people that don't have the virus yet. Okay. So when the number of people that have the virus reaches 1,000, what's the rate of virus spread? 0. Makes sense, right? Okay, I like it. You guys, am I with me? Now, if I were to solve this, true. Let's see. Did I really want to solve this right now? Maybe we can solve it. If we have to solve this, what would I have to use? Did you guys tell ahead of time? So let's see. What's x of 0, by the way, in this problem? What's the initial amount? 1. If I were going to solve this, and again, notice how this is once again autonomous, right? And this would be everybody's favorite. If you wanted to solve this, this would be, what would I have to do? Partial fractions. I love it. So to save us from that, I don't know why I didn't write this down. I'm not going to do partial fractions, but I do want to put this up here if I can find it. Was it in here, or did I get it from somewhere else? Shoot. I might have got it from somewhere else. Yeah, you did, Jeff. Oh well. The solution to this is going to have natural logs. You all agree with me? So just pretend for a moment that it came out to be something like this. It would probably have a minus somewhere. You're going to end up getting one of these logistic. And it makes sense. I mean, what's the ceiling going to be? The ceiling is going to occur at some time, but the ceiling is going to be 1,000. We're going to actually reach it, right? At some point. At some point, it's going to be everybody gets in there. Now, obviously, what variables are missing? Very quickly. What variables are missing to make this a more robust DE?
Like physical contact.
Physical contact, exactly. There's got to be a variable in terms of an estimate of the amount of time people are near to each other, right? What else? What about the people that recover? Could it be reinfected? Can you imagine how much more freaky this equation is going to get when you have all these other variables to throw? Then the question becomes, is the model good enough ignoring some variables? And that does happen. You guys kind of with me? So for example, the weather. There's a lot of models that do it, and some of them ignore certain things because it's been seen over time that ignoring certain things doesn't really affect things too much. It's just that when a hurricane turns, all of a sudden they're like, what the shit just happened? It's the things they ignored suddenly ganging up and making a big change. I don't know if you guys are with me. Maybe. Okay. This is beyond what we have to worry about. Okay. So I think that's all I wanted to say about chapter 3. So I'm going to leave it up to you if you want to try chapter 3 out. The way I do extra credit, by the way, for homework is it basically a 1-for-1. So if you don't do a section and you do an extra credit, it just gives you credit for the missing section. If you do all the homework and you do extra credit and get it right enough, you can have a higher than 100% homework average. You guys with it? WebAssign people, I've already put chapter 3 up there, I believe. Is that true? Where's my WebAssign people? Yes? So I'm not going to do shit to it to make it become extra credit. Just know that I know it's extra credit. By the way, the grade you get in WebAssign doesn't mean a damn thing. I need you to understand. When I look at it, because people doing homework out of the book. Have you guys gotten something back that said okay and there were actually mistakes? Anybody? Yes, you have. I know you have because I did it. Okay. So I allow you to make a few mistakes, especially if they're not huge. If you said 2 + 3 was 6 somewhere, I'm pretty sure you don't believe that. It's just a little brain fart, so you're fine. WebAssign, same thing. You don't have to make 100% to have a full grade homework. You guys kind of with me? I kind of know which problems are sort of like more important, and if you miss those, I might give you half credit if you miss enough of those. Does that make sense? Okay, that's a lot. Okay. So what I want to focus on today is, and this is going to get us back on track a little bit, get into chapter 4.
You put 3.1 on WebAssign.
I didn't put 3.2 yet?
Yeah, 3.1 is there, 3.2 is there.
All right, do me a favor and shoot me a note. I'm planning on actually logging into WebAssign soon, so. By the way, if you are in WebAssign and there's a chapter 1 or 2 section you didn't finish, just shoot me an extension request, right? Even though it's closed, I can reopen it for you. Does that make sense? And dear God, if you sent me a request and it's a week later, just send me an email and say, hey Waller, can you please just log into the damn thing, right? And I'm like, oh yeah, I can. I'm really sorry. I just don't, it's not part of my routine. Canvas, WebAssign, not a part of my routine. So you just gotta help out. So far, can somebody tell me what is true about every DE we've solved? Is there anything related? First order, I love it. So of course, chapter 4 is all about higher order differential equations. Do I want to do this? Here is something that I might start doing more of. I'm just going to give you this, and then we're going to talk about all this. Let me make sure I didn't want to say something more generally first. Maybe not. Oh, yeah, let's do one thing before I get to C. Do you remember, so before I give you this paper, existence and uniqueness. Just reminding us, the only types of DEs we've discussed this for are first order. This could be something you didn't realize at the time, but just to remind you, here's the version of a DE where we got what F was. So who remembers what you have to check? 2 things. Where is
The function, or that continuous.
where is F continuous, and where is partial with respect to Y continuous? Can anyone tell me the way I've written this, is this linear? Slightly trick question, maybe, I don't know. This is some function of x and y. Couldn't this be x times cosine y? That's a function of x and y, yes? So is this linear? No. So the requirements that f be continuous and partial of f with respect to y be continuous were more stringent than they have to be if I know more about it, because it's got to cover every possible situation that could be written like this. So the first thing we're going to study in chapter 4 is linear higher order ODEs. Right? The nice thing with that, if I have a linear nth order ODE, the nice thing about the requirements is they become much simplified, because I don't have to cover every possible situation that could occur here. So all that has to be true for this to have an existence of a unique solution is all of the coefficient functions have to be continuous, as does the function that they all kind of like equal. Y triple prime, Y double prime, blah, equals some function. So if those are all continuous, right, especially at where the IDP is, this is the X naught, Y naught. So let me give you this paper, that might make it easier. I don't want to write all this stuff down. I've already got it written down. Actually, there's 2. This is going to suck a little bit. I don't do this very often, but there's kind of a lot in this first section, so I thought this would be a good idea. I think that Chris was Yeah. Germans are in our future.
But that might have to be like, I have to look at what
Okay. I wanted to try to do this on its own, but it's just easier if I have all this up here. Oh, this will probably be good. That'd be amazing. So chapter 2, we learn all this business here. Chapter 4, we want to focus on linear DEs of order 2 and up. We've actually looked at some where you just had to verify the solutions. So one of the most basic, I got to turn my camera, but I'll do it in a second. One of the most basic second order DEs that we actually can solve right now, we already did solve it, which kind of highlights some of what we're going to talk about in here. I'll come back to the existence uniqueness in a second because I got all this stuff printed out up here. It's nice. Is this guy. So if you think about what that says, the second derivative of a function plus the original function is 0. So what that really says is the second derivative is the opposite of the original function, right? And of course, what functions do that? Cosine sine. So by itself, do you agree then that this is a solution to that DE? Do you agree with that?
Yeah.
Totally. Do you agree that this is a solution?
Yeah.
Yes. What about this? Why would that be a solution also? Ooh, I like it. That's something we're going to come up to. Well, I'm not even going to say that yet because we can all tell. You can't do something to cosine and make it become sine just by multiplying or dividing or adding. You can't make it become, you'd have to phase shift it, right? Which is a different thing entirely. So yeah, these are independent. That's going to come up later. So really, what's the most general way I could write the solutions to this here? We've done this already. C1 cosine x plus C2 sine x. So if I'm given an initial condition, and they have to be a set of initial conditions, right? So let me see if this makes sense. The higher the order of the DE, the more information I need to figure out. Because how many unknowns do I have here? 2. So giving you one piece of information is not going to be good enough. Right? If I only know that y of 0 equals 3, I can only figure out one of the constants, correct? So it'd have to be given, and very often I could either be given what the derivative at 0 is, 2, sure. I could be given another, that would be boundary value problem, but I could be given both derivatives at different places. So this would be an IVP, initial value problem. Notice that both of the pieces of information relate to a single input. What's the difference with the boundary value problem? Inherent in the name, I'm given one piece of information here and another piece of information there. So if I wanted to make this a boundary value problem, I could tell you maybe y of 0 is 3 and y of 5 is 7. I can tell you y prime of 0 is 3 and y 5 is 7. I can tell you y prime of 0 is 3 and y prime of 5 is 7. I can tell you all those different things, yes.
You can make a system of equations.
Say again?
Make a system of equations.
Yeah, in order to solve?
Yeah.
Yeah. No matter which situation I'm in, I'm gonna have to make a system of equations, correct? You guys all with me? Well, not really in this case, but in general I might. This one's nice because what happens when I put a 0 in? Which dies? Sign dies, of course, right? So, yeah. But in general, I could end up with a system of equations no matter which thing I've got. Is that okay so far? We've seen this before. We solved for constants before, not a big deal. Okay, so let's come back to this. It's just to show you, we've already done a second order. This is silly easy. Do I pick up the trivial solution, by the way? What's the constant solution?
Y is equal to 0.
Y 0, and that would just be a choice of both of these could be 0. I love it. Okay. Turn you around. What else put you here? So I'm given this. It's always nice to see a full guy written out. Here's the IVP. So if I have n derivatives, I need... Now let me ask you this. How many pieces of information are here? I'll wait for this to be a trick. It goes up to n minus 1, but doesn't it also include this guy? So there's n pieces of information, right? So if I have a second degree DE, in order to possibly fully solve it, I need 2 pieces of information, TCAS. Okay. Here's the existence and uniqueness. Notice the difference from before. When I say before, I mean back from section 1-2. So again, in section 1-2, we were dealing specifically with first order, did not have to be linear. And that's why it was a little more involved. It involved the f and the partial of f, right? It was more involved because there's more to consider, more possibilities. Here, if I restrict it to be linear, much nicer situation happening. I just need the coefficients and the function that it's equal to be continuous on this interval that includes my initial value and initial point. You guys with me so far? One of the most important things, though, is that. So obviously, if an is 0, I'm not working with an nth order D, I'm working with an n minus 1th order, right? You guys all with me? Which would adjust how many initial values I need, so forth. You guys with me? That's not what that says. That says a and x must not be 0 for every x in the interval. So if there's a single input that would make the initial coefficient 0, I'm not guaranteed that a solution exists and that it's unique. Let me stop for a minute. You guys semi with me? Okay, maybe. So for example, here is an example. That's why I don't like working on the overhead. Oh, there it is. Perfect. Here, beautiful paper. If I have this DE, somebody tell me everything you know about this DE. There's several things you could tell me right now. Yeah, second order. I love it. Is it linear or nonlinear? Linear, cool. I don't have to say linear in y because the way it's set up is dy dx is understood y is the dependent variable, so it's linear. Is that cool? Anyone else tell me anything else? What's one solution to it? Can you tell me one solution to it? You're sitting there like, you haven't told us how the hell to do that shit, Jack. Yeah. Interesting. Okay, so I like this. You're thinking ahead about. Now you gotta be careful. Let me see if you guys are really cool with this. Okay, one level of looking at this. We don't know how to solve this yet. We're obviously eventually going to learn how to solve this. I need you to realize, see how it says, And I know I keep looking there, I'm sorry. This freaks people out when I do that because there's a TV with it. See how it says, the original function is like terms with x times the derivative of it. Do you guys see what I'm saying? Because the only freaking way I'm going to add this shit together and get a number is if I've got like terms. Yes? You guys kind of with me? Or if everything's freaking 0 or some number. So I like what you said. This is perfect. You're thinking about what kind of function would possibly work here. Does someone have like an idea of what might work here?
We could make it into like a polynomial.
Say again?
Make it like a polynomial.
Why would a polynomial work?
Because
What happens when I take the derivative of a polynomial? Let's just say a power function, like x to the p. I lose an x, correct? So you see how every time I take a derivative, the dE multiplies it by the x that I lost. Wouldn't it end up being all like terms then? You guys follow? You guys follow? Now again, not every dE do we have to know ahead of time what's going to happen, but the idea behind solving this specific one is guessing what the answer looks like, and then throwing that shit in and seeing what happens. So if we guessed the solution to be x to the m, we could throw that in there and see what happens. And why does it make sense to guess the solution looks like that? Because when I take a derivative of a power function, it loses an x, and this dE is giving that x back. If I took two derivatives, I will have lost two x's. This dE gives it back. Do you guys see that level of this? To solve this, do you have to understand anything I just said? Not really, of course. But the more you understand what I just said, the more it makes sense how we solve this thing. Okay. So, just to kind of point out what's happening, section 4.1 is going to be like chapter 1. Do you guys remember chapter 1, we didn't really solve anything? Okay, all right. And that can get a little frustrating, but I don't know, let's just, real quick, guys, help me out. Just to state some of our desires for some freaking answer. Y equals x to the m, what's y prime?
X to the m minus 1.
What's y double prime?
m squared minus
Careful. Oh, I see what you did, okay. So it'd be m times m minus 1, x to the m minus 2, okay. So yeah, m squared minus, I'm with you, okay. If I put this in, I'll get x squared times m squared minus m, x to the m minus 2, minus 2x times m x to the m minus 1. Should be a minus, become a minus arg. Plus 2 times the original guess. And here's the thing though, here's the one little thing I shouldn't really be doing this, but it's too bad for me. What is the constant solution to this? Can you guys see it? Yeah, y equals 3 is a constant solution, is that cool? If y equals 3, 2 times 3 is 6, and these are both 0. Okay. So what we're going to learn later, and for some reason Jeff is telling you right now, once I figure out the constant solution, I just need to figure out what makes it 0. And the reason that is whatever answer I get here, I'm going to add 3 to it. And that's going to make the 6 show up. So there's some stuff I could do here, correct? Don't I get all of these fill in these? So don't I get a bunch of x to the m's for every term? Yes? You guys with me? You guys see that? This will be x squared times x to the m minus 2. Is that x to the m? This will make x to the m. This is x to the m. So I can factor in x to the m out. And then I get m squared minus m minus 2m plus 2. What's this? Yeah, how do I solve this? Can x to the m equal 0 no matter what x is? Is there any way to make that happen? No, I can't raise a number to some power and make it become 0. That's impossible. That's why the exponential has a asymptote of 0. You guys all with me? So the only way this could be 0 always is if this is 0. And of course, how do you factor this? Say it again.
-1 and -2.
Yeah. So I get m equals
1, 2.
1 and 2. Now, where did m come from? What got this whole thing started? Or guess. So what is one solution to this?
X.
X. What's another solution to this?
X squared.
Right? So m is the power of an answer. We got a power of 1 and a power of 2. So what is the solution to this? Same thing we did earlier with the sine and the cosine. Would constant multipliers mess this up at all? No, the constants would just come for the ride, right? I need you to understand, if I put a constant in, if I made y equals c x to the m, wouldn't the c just be present in every single one of these? And when I get to the point where I'm saying it's 0, it would just divide away. It wouldn't mess anything up. So couldn't this be any constant multiplier of x plus any constant multiplier of x squared? And how do I make the 6 show up? If I make this 3. Now, how would I figure out what the coefficients are of these two?
You need to know the initial condition.
Yeah, try to use the initial condition. Initial condition. Now, real quick. Do you have to understand every single thing that just happened? No. But I couldn't stop myself, and I'm sorry. Because that's one of the coolest things, is the fact that not all the time, but very often we will be able to guess what the answer looks like based on what's happening in the problem itself. And the beautiful thing, one of the best things I ever saw in my life as a student was, just try it. Say, okay, the answer is this, and then see what that leads you to. So this becomes a method to solve this. This, by the way, is called a Cauchy-Euler differential equation, if you want to know. 2 people that did way too much and left nothing for everybody else. Well, except for Gauss. He did a lot of shit too. Anyway. So, real quick. If I try, now, can somebody tell me, based on what we just talked about earlier, about existence and uniqueness, does this pass the requirement to guarantee that a unique solution exists? Are all the coefficients continuous? Each coefficient is continuous everywhere, correct? So, especially 2. It's a constant. That's awesome. You guys are with me?
Yeah.
Is the coefficient of the highest order term, is it not 0 anywhere around our initial point? What is our initial point? What is our input for our 2 given pieces of information? 0. What happens to the first coefficient at 0?
It goes to 0.
It's equal to 0. So that's a huge part of the existence uniqueness theorem, is all of your parts have to be continuous, check. All the coefficient functions have to be continuous. The function on the right side has to be continuous. It's 6. That kicks ass. Check. And the coefficient function in front of your highest degree term cannot be 0 anywhere around your initial point. Fail. It is 0 at 0. Does that mean there's no solution? No. Does that mean that there's no unique solution? No. It just means I don't know. It means I don't know. So let's see what happens. It could be anything. I think you all agree. It seems we've gotten a solution at least, right? We don't know if it's unique yet. I really want you guys with me. So this existence uniqueness theorem for linear higher order DEs is simpler than the one that we talked about before, because when I say linear, I am restricting a lot of things that could happen. So I don't have to consider as much. It just boils down to continuity of all the various coefficient functions, and the first one can't be 0 anywhere. So let's see what the ramifications are. So our solution we got so far looks like this. And And our initial conditions are y of 0 equals 3 and y prime of 0 equals 1. Do you see how y of 0 equals 3 is not helpful? That's like, thanks. So if y of 0 was anything other than 3, if I made y of 0 2, is there a solution to this? I want you guys to know, if I made y of 0 2, if you input 0, what do you get? 3. So if I said y of 0 had to be 2, is there any way to make that happen? No. So that would be no solution. Why is that okay? Because x squared screwed us over, right? It's 0 at the freaking 0, that's something. But y of 0 equals 3 works, because one solution is y equals 3, correct? So y is 0, 3. Awesome. It just doesn't tell us anything about the constants. What about, can you guys figure out real quick, what does y prime of 0 equal 1 tell you? Can you do some work? Figure out what that tells you. What's y prime? C1 plus 2C2. X. You can do it, Jeff. So y prime of 0 is C1, and that's 1. So all I know is y equals x plus C2x squared plus 3. That is what I know. So does a solution exist? Yes. Is it unique? No. Why? Because can you make C anything you want it to be? Yes. So you get you get an infinite number of solutions, right? Yes, kind of with me. Yes.
So if there's also a restriction on C2, then it would be.
Yeah, if only I would have said, like y prime of 0 equals 1, y prime of 1 equals 3. I could have solved for both coefficients, right? Yeah, so it is dependent on the IVPD, the initial condition that I give. You guys with it? So existence uniqueness is fundamentally tied to the initial point I give us. In fact, if the initial point had nothing to do with 0, x squared being first would not mess me up at all. Is there a neighborhood around 1? If I made my initial conditions based on an input of 1, is there a, these are both 1. Is there a neighborhood around? Sure, Jeff. Hunt the wascally wagon. Is there a neighborhood around 1 that does not include 0?
Yeah.
Hell yeah. Have you guys ever heard the phrase neighborhood to talk about math? Neighborhood just means like 1 plus h, 1 minus h. Little neighborhood, right? It's a little interval around 1. Can you draw an interval around 1 that does not include 0? Yes. So I would be guaranteed a unique solution exists if these would have been based on 1. Because does the original coefficient of the highest degree become 0 anywhere around, in the interval around 1? No. Let me stop for a minute. Okay. All right, Jeff. Rein it back in, buddy. Coming back to this. So that was an example of a situation where this was violated and we got multiple solutions, not a unique one. And with one little tweak, I could have made it have no solutions, right? Man, time flies. You talk a lot, Jeff, I know. Blah, blah, blah. So there's a very easy one. This is awesome when all the coefficients are constants because cookie did. This one, I say done in class, but I mean, if I gave us these conditions and I tell you this is the solution. And by the way, somebody said this earlier. Do you guys see, real quick, do you guys see why it makes sense the solution to this is going to be e to a power? What does that dE say? Must be true. In order for me to be able to combine these and get 0, what must be true about those functionally? You can do this, you can do this. No, that's one possibility. No. Well, why? That would make them like terms. Good, they have to be like terms. So you need a function whose derivative doesn't fundamentally change. I need you to be with me on this. That equation says I'm able to combine the various derivatives of y, and they are able to actually be put together. They must be like terms. What's the only function, well, what's the main function that we know of whose derivative is itself? E to the x, right? No, actually no. Just want to leave it open for a minute, but no, it's not. So it makes sense. So this would be another situation where we could guess what the solution is. I would guess the solution is e to the mx. And now I plug that shit in and see what happens, right? Last thing I want to say, because I'm running out of time, because I just talked way too freaking much. I got to remind myself I talked about chapter 3 too, so that's not bad. Boundary value problems, like I said earlier, it could satisfy the requirements of the existence, but anything could happen for a boundary value problem. The existence uniqueness is only true for an IVP, not a BVP. IVPs just mean that everything is dependent on the same input. These are both based on 0, that's an IVP. These are situations where they're both based on a different number. That's why we call it a boundary value problem. Okay. So, just to give you a little preview, this is one of the most evil things ever. I didn't want to say this earlier because I just want to save the pain for now. Remember homogeneous? And the definition was if you replace x with tx and y with ty, blah, things happen, right? That's the general gist. We're going to talk about homogeneous DEs, and that word means completely not what it meant earlier. It's now going to mean nth order linears that equal 0. That's a homogeneous DE, nth order DE. I put a little note. This is one of the most exciting things about all of mathematics is when this kind of thing happens. Note, we're defining the word homogeneous in a completely different way. We weren't around to suggest otherwise. So too damn bad for us, right? Okay. You guys semi with me. This involves the thing I said earlier about if I solve for the constant solution, or if I solve for the thing that makes this work, I can then solve for the thing that makes it 0, and we'll talk about why next time. That's too much. So we'll pick up there on, what day is it today? Wednesday? It's Tuesday? Okay. We'll pick up on Thursday. Okay.
So the new homogeneous, does it still satisfy?
No. Okay. There's no requirement for it to satisfy that requirement. So the thing is, there's something called a homogeneous function, which we borrowed that for the earlier thing we talked about. Homogeneous differential equations are actually, there's any differential equation that equals. And the non-homogeneous, just wouldn't. I wish we would have just picked